first technical talk of today. As you heard earlier when I was talking about the agenda, we're joined here by Megali. She is at the University of New South Wales in Australia and been doing fantastic work in building federated systems. And so I can't wait to see what she's found, what she's learned, what she can share with us. So over to you, Megali. I'm super interested to see your work.
Yep. I'll share my screen.
Yeah, yes, please.
I hope it's visible.
Yes, looks great.
Okay. Hello, everyone. I am Megali Nandi, and I'm really thankful to Dick Lane for inviting me for this talk. I'm here to present our work, Nosy Layers Noisy Fixes, Tackling DRAs in Federated Learning Systems using Explainable AI. This work was accepted at the 28th ACM Asia CCS conference, which was held last month. I'm currently a PhD student at UNSW Sydney in the CTI lab, and I'm under the supervision of Dr. Faraj Sharagi and Dr. Sanjay Jha. And I've also collaborated with Dr. Nazatul Sultan, Gustavo Batista, and Raymond Zhao from CSIRO. So what I'll be covering is, first of all, I'll be just giving an overview of federated learning and the current data reconstruction attacks. That's the DRAs. And then this paper was on defenses against DRAs. So I would be describing about why the current defenses fail and the problem statements that we have tried to solve. Then we come to our solution. That's the Dr. Armor and the results of Dr. Armor. Starting with what is federated learning is, federated learning happens across 3 rounds. First is the model initialized. A model is initialized by the server and it's sent to the clients. The clients updates the model and trains on the local data and sends the updates to the server. The global model in the server is updated using the weights sent by these clients. Now, whenever there is a system that's launched over the internet, the next news we hear is there are some attacks happening, right? So even for federated learning, we have 3 kinds of attack scopes. First is the client side, the second is the server side, and the third is during the communication between the client and the server. Here we are working on a server side attack, but the defense is from the client side. So one of the server-side attacks is the data reconstruction attacks, where the server is the entity, malicious entity. So the server, when it's sending the model to the clients, they basically do some modifications on the model, which can be used to give out the weights from the clients, and those weights can be used by the server to reconstruct the data. So that is the data reconstruction attack. And why we have this nosy layers is influenced by one of the recent attacks, that's the low-key attack, where the malicious architectural components are added to the layers of the models and sent to the clients. Now, the effect of the DRA is it can reconstruct the data and also identify the client from which the data has been coming in. The DRA works because the gradients from these malicious layers can be used to reconstruct the data, and the current existing defenses do not work because the attack remains effective even when the aggregation is in place. Now, coming to the image on the left-hand side, this is the low-key attack. So they have the convolutional layer, which basically helps in the identification of the clients. And then we have the convolutional output, the FC1 and FC2. The 3 layers which has been added by the malicious server and the data used, coming out of these outputs can be used for the reconstruction of the images at the server side. So why existing defenses fail against this attack? We have multiple defenses like the secure aggregation, Byzantine resilient aggregation, anomaly detection, differential privacy, gradient compression and pruning, and limiting mutual information. All these types of defenses basically tries to make the updates or the weights sent by the clients in a secure way. Like using monitoring or basically identifying what kind of outliers are there. But however, all these kinds of defenses were surpassed by the low-key attack. Now, differential privacy is one of the defenses which will work for any kind of attack However, this will lead to accuracy degradation because there is a costly trade-off between the privacy and the utility. So why addressing these attacks is crucial? Federated learning was launched because we needed the security and privacy of the data, which is existing in the client nodes, right? And we also need to have the performance of the global model to remain effective, and the accuracy and effectiveness of the global model should be maintained. So, because of those reasons, we need to address these attacks. Now, with that, we come to the two problem statements that we have tried to solve in this work. First is we need to identify the malicious layers that's involved in the DRAs. And second is after identification, we need to defend against these DRA. So here we have basically tried, the motivation is when federated learning was launched by the Google. So they said that whatever model is sent to the clients would be acting as a black box. So whatever the server sends to the clients, they would be training it on their own data and sending the weights. Now here we have taken a completely different approach. We have tried opening the black box. We are trying to give the control to the client, treat the model as a white box, and we are trying to understand the layers of the models and how they are contributing to the output of the original model architecture. So coming back to the low-key attack, here we have these, suppose this is the model architecture, the original model architecture, and the first three layers have been added according to the low-key paper. And these are acting as the malicious layers. And this is the original model architecture with the output layers, which will act as the non-malicious layers. Now, suppose this model is having this image as the input and it outputs cat as the output. Now, these three malicious layers are because these are malicious and they are leaking gradients which are used for reconstruction of the data. These three layers are not supposed to be contributing to the output of cat. Rather, the layers which are used in the original model architecture should be contributing to this output, right? So that is why. How we can solve whether a layer was able to contribute to the output or not is using the XAI, that's the explainable AI. So we come to the first solution, that's the explainable AI. It basically refers to the methods and techniques that make the results of machine learning models understandable to humans. It gives us trust and transparency. It mitigates any kind of bias in the AI models, and it's also user accepted because it gives clear explanations for AI decisions. Now, the methods used by this work, because it's the first work using explainable AI on DRS, we have used layer-wise relevance propagation, that's the LRP, and deep Taylor decomposition, that's the DTD. We have used LRP for smaller datasets and smaller models, and we have used DTD for larger models. The reason for this is properly explained in our paper. Because we have a constraint in time, I'm not going to go into the details of this. Now, this is a layer-wise relevance propagation where we have the cat as the output and we go from backward to forward. So basically, we're going from the output to the input and trying to understand how each of these layers are actually contributing to the output. So now, whenever the malicious layers, which are sending gradients, they are not contributing to the output, we can flag them and identify that these layers can be malicious. And that is how we were able to get the results. Now, coming to the PS2 solution, where this is the mitigation strategy, where we have identified the malicious layers. Now we need to give the control to the client on how to defend it, right, against the DRA. So we have proposed two solutions. First is the Nosy fix, where we have added DP, and second is the pruning layers. Now, one may argue that differential privacy is already existing. What's new in this? Now, here I would give the argument that we have added one extra step here. Differential privacy in normal federated learning systems is added to all of the layers outputs, right? Now here what we have done is we have identified which layers are malicious and added DP to only those malicious layers. In that way, we do not care if the privacy utility trade-off of those layers are affected or not. So in that way, we have used the Nosy fix, that's the differential privacy. And the second is the pruning layers, where we have added skip connections to the non-malicious layers. That is, we are completely skipping the malicious layers training and just adding skip connections to the non-malicious layers. So these two are the solutions for the mitigation strategies. Coming to the results, first is how we have detected of the malicious layers when the layers are at the start of the model. So these red marks are basically the malicious layers, and we were able to use the explainable AI to show that these are the malicious layers, whereas the rest of them were not. This is a detection of the malicious layers when it's towards the middle or towards the end of the model. This was randomly generated, and again we see that with using by the red flags, we are able to detect the malicious layers. Now, the mitigation strategy was the adding the noise. So we have used pixelation here. One of the results was pixelation, where this is the original images, and this is the DRA using the Loki paper, and this is the pixelated images. We are not able to understand what the images are. The detection reliability is where we have found that the TPR and TNR across the 5 datasets that we have tested on are pretty good. However, when we come to the detection reliability, when 3 malicious layers are inserted deep in the model using these explainable AI systems, we see that for ImageNet we have a little lower TNR and TPR values. This is because we have used LRP in the larger images in the largest data sets, which is the ImageNet, and the model structure was also pretty large, because of which the TPR and TNR were reduced. However, we have also proposed that when we use much more complex explainable AI systems, these results are actually able to improve. Now, the impact of Dr. Armor on the FL accuracy, we wanted to check how our defense is actually affecting the FL accuracy. So this is the Dr. Armor with the noise and the Dr. Armor with pruning. We see that there is a slight decrease in the accuracy, but we have argued that with this, we are able to get the required utility of the system rather than leaking the data from the client devices. This is a poisoning impact on the accuracy of Dr. Armor, where we have tried using continuous and periodic poisoning, and we see that even with continuous and periodic poisoning, we are able to use the Dr. Armor, and the accuracy of the models were completely increasing and not getting affected by the poisoning. And here we come to the comparison with other defenses, where we have compared our work with the normal pruning, DP Laplace, Guardian, DP Gaussian, and Soteria. And we see that this is our Dr. Armor, and we are able to leak pretty less number of images, and the leakage rate is pretty lower to the rest of the defenses that were already existing. And the main reason is because we have tried to identify the layers. The rest of the defenses were trying to get privacy utility trade-off on their systems. But here we do not care about that. We have already identified the malicious layers, and then we have done the defense. So that's the reason. So coming to the conclusion, the motivation behind this work is that current state-of-the-art DRAs make model modifications. So basically, these make the models detectable on the client side. And how we are detecting is we have given the control to the client to treat the model as a white box and use explainable AI. And after identification, the mitigation strategy was to add differential privacy or prune those layers only to the identified layers. Now, once that we have done the defense, the next frontier that we are working in our lab is to design a stealthy and undetectable threat, which can evade detection and break any kind of existing defenses against this DRA attacks. So that's it. If you have any questions, thank you for listening.
Thanks so much. It's really interesting work. I love the fact that you've also open sourced it, and actually you've got the links that early on in the talk and also on the slide here to your project. We actually have a question already about this in the webinar. I would just say also, as a reminder, if you happen to be dialed into the webinar, feel free to raise your hand and you can ask your question with audio. I'm going to check out this question in a moment. Or if you happen to be in the Flower Slack, and I also will check the YouTube and other channels momentarily. But let's get things underway with this question. It says, did you experiment with structured data leakage? And so that's the tabular data. As far as I know, there is a tab leak attack for tabular data?
Yes, so we have not tested it against a tablet data attack, but this kind of defense will work for any kind of data leakage from any kind of federated clients, because we are not assuming what kind of model is coming from the server. All kinds of assumptions from the server is taken care of. And regarding structured data leakage, we have tested with image datasets and text-based datasets, and we were able to defend against them. But yes, I am open to test it against a tab leak attack as well. Thank you for the suggestion.
Okay, that's a good answer. There's actually another question here. It is, the question is the malicious layer added to all clients' local models or a subset of the client's local models? If it's added to a subset, then won't it make the aggregation difficult due to hetero local models among clients?
Okay, so this we have to shift towards the server side, because the malicious layers are added to the client's local, to the global models actually. Now, whether the model is added to all the client models or not is something which the server, which is the malicious entity, would be able to decide. However, if it's added to one of the subsets, we have to remember that the server is the aggregator and the server is the malicious entity. So now, even if the server gets the low updates from these malicious layers from the clients along with the non-malicious layers, the server can always has the rule upper hand here, right? Because the server will always be able to use only the ones that's needed for the global model and update it. It can basically remove the ones which are the updates from the malicious layers and use it for just the data reconstruction, and use the updates from the non-malicious layers for the global model update. So again, we have not made any such assumptions, but that is how the DRAs actually work.
Okay, that makes
I have
sense.
answered the question.
Yeah, good answer. Let me just see. I'll look in our Slack here. We've got some questions. 1 second. Oh, I see. Yes, this is a sort of a general question, and it's asking. Let's see. It's basically asking, what are the types of attacks you think you are not able to cope with at this stage? The ones that you sort of about that worry you. If somebody wants to deploy this in a very high importance scenario.
Sorry, I didn't get the question.
Yeah, I probably elaborated too much. The question is just saying, what are the attacks that you can't defend against currently?
Okay, so this is defense against the data reconstruction attack, and the current state-of-the-art attacks are the low-key, derobbing the Fed, or any kind of gradient inversion attacks. So this defense will work for any kind of data reconstruction attacks right now. We have the project GitHub, and you could use any data reconstruction attack and deploy this defense. I hope it'll work. But for any other kind of defenses like the membership inference attack or any other kind of attacks that's happening on federated learning systems, maybe this defense won't work. But yes, using explainable AI for modern architectures can be a scope for further research.
Okay, I see. Great. Well, I don't see anything else here. So that's great. Thank you so much for the presentation. Great work. And thank you for building on Flower. It's a great stuff. Amazing. Thank you.
Oh, yes. Thank you.